So this is from Section 2, Topic 6 in Algebranation. Section 2, Topic 6. And I'm going to take all of the graphing parts of the notes actually on graph paper. If you want to take it on regular notebook paper and then just have the graph paper for the actual graph, that's okay too. This section is called Investigating Graphing, Substitution, and Elimination. In this video, I'm only going to do the graphing part, and then I will make like a part 2 video for the rest. So I'll call this part 1. On Algebranation, it's all one video. It's all one section. But because we're kind of getting started late in this class, I'm just going to do the graphing part today. And then we'll come back to the substitution and elimination next class. Okay? So we are going to be doing solving systems of equations. And you were supposed to have covered this in Algebra 1. Maybe you did, maybe you didn't, but I'm going to teach it just like you've never seen it before, okay? Like you've never learned it before. So, when you solve systems of equations, that means a system means you have more than one equation, okay? And to solve it means graphically, where do these two, say we're solving a system of linear equations, so two lines, so where do these two lines intersect? What ordered pair do they have in common? Or do they not have any ordered pairs in common? Or are they the exact same line and they have every ordered pair in common? So when you're solving a system of equations, you are trying to find the ordered pair or pairs that make both equations true, where they intersect on a graph, okay? There's 3 different ways to do it: by graphing, by using substitution, and by elimination. So today we're just going to do the graphing part, right? Graphing's helpful if you have graph paper. If the graphs are easy, say you don't have decimals and fractions and all that stuff, weird slopes, they're easy. But it's not always the most convenient way, all right? Sometimes it is, sometimes it isn't. So in example 1, we're going to solve a system, and that bracket kind of lets you know that you got a system coming. We have x plus y equals 3, and we have negative 3x plus 2y equals negative 4. And my directions say solve the system of equations by graphing. Solve the system of equations by graphing. So on this first one, I'm going to show you 2 different methods of graphing these linear equations, okay? They're both given to you in standard form. So what you could do is you could convert them both to slope-intercept form and graph them that way, or you could find the x and the y intercept on each equation and graph them that way, like we did with those word problems, remember? Either way is fine, okay? Sometimes one way is going to be more convenient than the other way. So for our purposes today, and this first problem, I'm going to show you both ways. So method 1, I'm going to graph by finding the x and the y intercept, okay? So first thing I'm going to do is I'm going to make a little graph over to the side so that I don't run out of room to include it. And if you don't have a ruler, of course you can use your ID. So method 1, I'm going to do in pink. In this method, I'm going to graph the line by finding the x and the y intercepts. So I'm going to do that for each equation. Okay? And on this first one, I'm going to write the instructions out very detailed. And in the other examples, I'm not going to write every single thing out. But this topic is so important in Algebra 1 and Algebra 2 and college algebra that I want to really make sure that you know what you're doing. And if not, you have this to refer back to. Okay? So to find the x and the y intercepts, I'm going to first use that top equation. I'm going to do this for both of them. Okay? So I'm going to start with x plus y equals 3. To find the x-intercept, comma, substitute a 0 for y and solve for x. So remember on Algebra Nation they did that. So what he did, we watched Darnell, that Darnell video. If you substitute a 0 for y, so all he did was cover up the term that had y in it, okay? Because x plus 0 equals 3, that term goes away, right? But on our paper, I'm going to put it in my notes. So x plus, instead of y, we'll substitute in a 0, equals 3. And we do that because any ordered pair on the x-axis, they all have a y value of 0. This would be 1, 0, 2, 0, 3, 0, 4, 0, right? So when I want to know where a graph crosses the x-axis, I know every ordered pair on that axis has a y value of 0. So when y is 0, what is x? So when y is 0, x is 3. So on my x-axis at positive 3, 0, I'm going to plot my x-intercept for that first equation. Everybody cool so far? Okay. Now for that same equation, x plus y equals 3, I'm going to find the y-intercept. So to find the y-intercept, substitute a 0 for x and solve for y. So same equation. Every ordered pair on my y-axis has an x value of 0. So if I want to know where my line crosses the y-axis, I say when x is 0, what is y? And in this case, you also have a y-intercept of 3. So now go to your y-axis, and at positive 3, when x is 0, y is 3, draw a line. okay? Now, I don't really know where these two lines are going to intersect, so I'm going to make my line pretty long because it may not just intersect somewhere between these 2 points, okay? And that has a slope of -1. So just keep that in mind when you're drawing your graph. So you can kind of make that as precise as you possibly can. So I've only graphed one line, okay, using the x and the y intercept. We also had that second equation, -3x plus 2y equals -4. We're going to use the same method to graph the second equation. All right? So same method, but I'm graphing the -3x plus 2y equals -4. And it doesn't matter if you find the x-intercept first or you find the y-intercept first. That doesn't matter because you have to find both of them, right? Okay, so let's just, since we found the x-intercept first above, let's just do that again. Find the x-intercept. So if we want to find the x-intercept, that means we have to get rid of the term with the y. To do that, we plug in a 0 because we know wherever the graph crosses the x-axis, it's going to have a y value of 0. So I'll have -3x plus 2 times 0 equals -4. We know 2 times 0 is 0. So instead of writing -3x plus 0 equals -4, I'm just going to write -3x equals -4. Bless you. Bless you. So divide both sides by -3. And x equals -4 divided by -3 is positive 4/3. Or we could say 1 1/3 or 1.3 repeating. Now on that, obviously we're going to have to estimate a little bit, okay? This is why graphing's not always the best option out of graphing, substitution, and elimination. Graphing's not always the best because it's not always the most precise, because like in this case, we have to kind of estimate where 1 1/3 is on the x-axis. So if we start at 0, we go over to 1 1/3 between 1 and 2, I'm going to approximate where that point is. So now let me find the y-intercept. And I'm running out of room, but I want to use this other space over here for my second method. So to find the y-intercept, we'll substitute in a 0 for x. So that'll be -3 times 0 plus 2y equals -4. We know -3 times 0 is 0. So basically that term just went away. And we have 2y equals -4. Solving for y, so we'll divide both sides by 2. And my y-intercept is -4 divided by +2 is -2. So on the y-axis, I will go to my origin, and -2 will be down 2 units. And I'm trying to be as precise as possible. So how many solutions is this system of equations going to have? One solution. They intersect one time. You're either going to have one solution, no solutions, or infinitely many solutions, okay? You can't have two solutions. These lines aren't going to change directions and come back and cross each other. Not when you have two lines anyway. If you had a line and a parabola, you could have two solutions. Okay, so the solution is the ordered pair where they intersect. So what is my solution? What is it? X equals 2, y equals 1, so that ordered pair is 2, 1, right? 2, 1 is the answer. All that work to find that solution. Ordered pair where they cross. So if I was to substitute that ordered pair back into both equations, it would make both statements true, which I'll do in a minute. But I want to show you the second method, okay? And the second method for graphing is the equation was in standard form, both of them. We could convert them to slope-intercept form and graph that way. Our graphs are going to look the same, all right? It's just another way to graph it. So method 2. Now, if your equations were given to you in slope-intercept form to begin with, I would just graph them like that. I would not try to find the x and the y intercept, unless you had like crazy decimals or big numbers or something like that. But otherwise, I would just graph them from slope-intercept form. So method 2, we will convert both equations to slope-intercept form. Convert both equations to slope-intercept form. In this example, they were both given to us in standard form. Sometimes you'll be given equations both in standard form, both in slope-intercept form, in no kind of form, okay? So you might have to convert it to one or the other. So for x plus y equals 3, that's my pink line. Slope-intercept form, remember, is y equals mx plus b. So you have your y isolated. So in this example, if I want to isolate the y, what would I do first? Subtract x from both sides. So I have x minus x is 0, bring down the positive y equals. Slope-intercept form has the term with x first, so that'd be negative x plus 3. In slope-intercept form, what does that plus 3 tell us? What is that? It's the y-intercept. What is our slope? Negative 1 or negative 1 over 1. It's not x. It's just that coefficient of x, right? It's the same as the rate of change. So your slope is negative 1 in this case, or negative 1 over 1. Rise is 1, runs 1, make sure it's negative. Okay, so we already graphed this line using the intercepts. Let's just see if this is the same thing. So we have a y-intercept of 3, 1, 2, 3, that's correct. A slope of negative 1. So rise of 1, run of 1, rise of 1, run of 1, rise of 1, run of 1. And it's a negative slope, right? From left to right, as my x's increase, my y's decrease. So same line, just a different way to graph it, right? Remember when we were doing the word problems homework and some of y'all couldn't remember how to graph lines that you learned in Algebra 1? So hopefully if you had forgotten, this will kind of jog your memory. All right, so let's do the same thing to the second equation, which mine was purple. So that is negative 3x plus 2y equals negative 4. I want to convert it to slope-intercept form. So I need to isolate the y. What would I do first? Add 3x to both sides. So on the left, negative 3x plus 3x is 0. Bring down your positive 2y equals negative 4 plus 3x. Those are not like terms. We cannot write it together. Slope-intercept form has the term with the x first. So that would be 3x, and it's positive, minus 4. Am I finished? No. What do I do now? Divide by 2. And since I want to graph this, you know how we can do one big line over 2? But since I'm graphing it and I want to easily see what my slope and y-intercept is, I'm going to do them separately. So 2y divided by 2 is y. 3x over 2, I cannot reduce 3/2, and that's my slope, so I don't want to change it to a decimal or a mixed number, so I'm just going to leave it as 3/2 x. Negative 4 divided by 2 is negative 2. So what's my y-intercept? Negative 2. And my slope is 3 over 2. And that's positive, right? 3/2. So when you're graphing, you always graph your plot your y-intercept first. So in the purple line, the y-intercept was negative 2. That's what I said. The slope is positive 3/2. That means you have a rise of 3, a run of 2. And I went to the right because it was a positive slope. If it was negative slope, I would have gone up 3 and left 2 to make a negative slope. Is it the same line that I graphed before using a different method? Yes. Does it matter which method you use? No. To me, if it's in standard form already, I'd probably find the x and the y-intercept. If it started in slope-intercept form, I would probably graph just in that form. You don't have to change anything. You just look at it and plot the points. Okay? So just let me show you what this means, and I'll do this on the back. This means that 2, 1 will solve both of these equations. When x is 2 and y is 1, I'm going to put this on the back, and like I said, in the next couple of examples, we'll go much faster than this. I just really want to take the time on the first one to overly explain. So we're saying that 2, 1 is the solution. That means x is 2 and y is 1. That should solve, if that's actually true, it will solve both equations, okay? So equation 1 was x plus y equals 3. If x is 2 and y is 1, if x is 2 and y is 1, does that make a true statement? Yes, 2 plus 1 is 3. Are there any other numbers that I could plug in there? Well, the graph, that's the only place the graph cross, right? So that should be the only two numbers that work for these two equations to be true. The other equation was negative 3x plus 2y equals negative 4. So when x is 2, that would be negative 3 times 2 plus, and y is 1, so 2 times 1. Notice I don't have any variables now, so I'm not moving anything to the left and to the right. I'm going to simplify the left side and see if it equals the right side. So negative 3 times 2 is negative 6. Positive 2 times 1 is positive 2. Does that equal negative 4? Is negative 6 plus 2 equal negative 4? Yes. It made true statements for both equations. That's always a way you can check your answer. Like, I don't know if I graphed them right. Well, if you graph them correctly, substitute that ordered pair that you're saying your solution is into both equations, and if they're both true, then you did it right. If they're not true or one of them's not true, then something's not right. Okay? All right, let's speed it up. Example 2. And I'm not going to do both methods for all of them either, okay? If you like one better than the other, then you do whatever you prefer. But for the notes, you might want to, do the same thing that I'm doing. But on your own, you can use whatever method you want. All right, example 2, solve the system by graphing. Remember, if you do not have your own graph paper, please get some, especially if you can get the 3-hole punch kind. Because I won't be able to supply people throughout the year. We do use graphs a lot. My system is 2x plus 2y equals negative 2. And the other equation is x plus y equals -1. Okay, these equations are both given to you in standard form. You can convert them both to slope-intercept form, or just find the x and the y intercept. It doesn't matter whichever you want to do. Me personally, since they're both in standard form and it doesn't look like I'm really going to get any fractions, if I find the x and the y intercept, that's what I'm going to choose to do. Okay? So my top equation, I'm going to do in purple. And I'm going to find the x and y intercepts. So I'll find the x-intercept first. So to find the x-intercept, that's where the graph's going to cross the x-axis. I know every pair on the x-axis has a y value of 0. So to find the x-intercept, I substitute in a 0 for y. That means the only variable I have left to solve for is x. So when y is 0, what is x? So basically you're just getting rid of the term that has the y in it, right? Like Darnell did in the algebra nation video, he just covered the term up and set 2x equal to -2. We're doing the same thing, but y'all know me, I like to show my steps because I like to write a lot of stuff apparently. But in your notes, I want you to be able to see how you got from one step to the other. So if I'm solving for x, I'll divide both sides by 2, and x equals -1. So for my top equation, I have an x-intercept of -1. In the same equation, I have to find the y-intercept. So every ordered pair on the y-axis has an x value of 0. So to find the y-intercept, I substitute 0 in for x and solve for y. So that will be 2 times 0 plus 2y equals -2. 2 times 0 is 0. So basically you're just left with 2y equals -2. If you're solving for y, divide both terms by +2, and y equals -1. So on my y-axis, I have a y-intercept of -1. Notice, what's your slope here? -1, right? So just think about when you're putting your straight edge and drawing a line, even though you don't have to plot any more points, it might help you to plot some more points using the same slope, or just make sure your ruler lines up. Because the more accurate you are on graphing, see mine's a tiny bit off, the better. You don't just want to willy-nilly draw a line, not use a straight edge. Mine's pretty good, but I could have been a little better. My ruler slipped there at the last minute. And sometimes your lines are not going to intersect at perfect lattice intersections, okay? Y'all know what I mean by that? Perfect lattice intersection. It's like on your graph paper where two of these, your grid lines cross. maybe it intersects like in between there, and you have to estimate what the solution is. That's another reason why graphing is not always the best method. Okay, it works fine when your two lines do intersect at a perfect lattice intersection, but if they don't, then you got to estimate. Then you're not going to be very precise. Another method would work better in that case. Okay, so we have not graphed the other line. X plus y equals -1. We haven't graphed that yet. So I'll do that next. I'll start by finding the x-intercept. So if we want to know what the x-intercept is, we substitute in a 0 for y. So that would be x plus 0 equals -1. So what is x? -1. So on my x-axis, plot a point at -1. They share that point. So maybe that's where they intersect. I don't know. We're not just going to assume that. We're going to keep going and find the y-intercept. So take your same equation. X plus y equals -1. And if we want to know the y-intercept, we substitute in a 0 for x. So y equals -1. Go to your y-axis, plot a point. They're the same. If I connect that line, or those 2 points rather, aren't they the same line? Even though the equations look different, they're the same exact line, aren't they? So what ordered pair do they have in common? What else? Is that the only 2 points they have in common? Infinitely many solutions, right? All real numbers. Every ordered pair on these lines, if I substituted them into both equations, they would be true. Only the ordered pairs on the lines, but every single ordered pair they have in common because they are the same lines, okay? So you wouldn't just pick these 2 ordered pairs, you would say infinitely many solutions, okay? So let me just write a little explanation up here. The solution, or I'm going to put in parentheses S, the solutions are, I guess you would say, infinitely many solutions. This means, comma, the 2 lines were the exact same line, so they have every ordered pair in common. Now let me show you something. On this one, I didn't show you both methods. We just found the x and the y-intercept, right? On the first example, I said you could also convert it to slope-intercept form and graph it that way. Well, if we would have used that method, I'll just quickly show you on the back. If I converted both of these to slope-intercept form, I'll just do that on the back. So the first one was 2x plus 2y equals -2. Remember, slope-intercept form is y equals mx plus b, right? So I got to isolate the b. This is when we did literal equations the other day, and we're isolating or solving for one particular variable. That's why we did that already, so we could easily convert these formulas if we need to, or forms. So if I want to solve for y, what do I do first? Subtract 2x from both sides of the equation. 2x minus 2x is 0. Bring down your positive 2y. Bring down your equal sign. These are not like terms. Negative 2 minus 2x are not like terms. Slope-intercept form writes the term with the x first, so that's negative 2x, and then a constant goes at the end. Is it in slope-intercept form? Not yet. I gotta isolate the y, so what do I do now? Divide every term by 2. So 2y divided by 2 is y equals negative 2x divided by 2 is negative x. Negative 2 divided by 2 is negative 1. My y-intercept is negative 1. My slope is negative 1. Which it was. My y-intercept is negative 1. My slope is negative 1. Okay? I just want to show you something. So the other equation was x plus y equals negative 1. Convert it to slope-intercept form, so that means I get the y by itself. What should I do? Subtract x from both sides. X minus x is 0. Bring down y, and it's positive. If it was negative y, bless you, we need to bring that down as well, bless you. So I would write this as negative x minus 1. Bless you. Y-intercept's negative 1, slope is negative 1. Do you see how when we converted it to slope-intercept form, they look exactly the same now, right? But when they were in standard form, they didn't look the same. But they were. It's just notice this one all could have been reduced by 2 every single term, and it would have given us the same thing as what we had in the other equation. So if we would have seen from the start they were the exact same line, we would have already known they had infinitely many solutions. Coolio. All right, let's do one more. Anybody have questions about this? Example 3. Oh, some of you that needed to borrow graph paper, I didn't think about needing more than one sheet. If you need some more, come up and get it from me. I'm recording this, so I don't want to leave my spot, but if you need some, I've got it up here. Again, we're going to solve the system by graphing. Solve the system of equations by graphing. And we have y equals 2x plus 3 and y equals 2x minus 6. Now both of these equations are already in slope-intercept form. So to me, and there's nothing weird, there's no decimals or improper fractions or nothing like that. The numbers aren't huge, so there's no reason why I would find the x and the y intercept on these and graph it that way, because I can just look at the equations and graph them from there. I don't even have to do any math, right? So when they're both in slope-intercept form, usually really easy to just go ahead and graph by plotting the y-intercept first and then a slope. So just so we have it in our notes and to review, y equals 2x plus 3. What is the y-intercept? 3. And you plot that first, okay? What is the slope? 2. And it's not a fraction, so remember that's the same thing as 2 over 1. 2 is my rise, 1 is my run, and it's a positive slope. So I know from as x increases, my y has to increase, right? So the first thing I do is I plot the y-intercept. A lot of kids go to the origin and they count the slope from there, and that's not correct. Not unless your origin is the y-intercept. My y-intercept is positive 3. So on the y-axis at positive 3, I'll plot my first point. And then from there, not my origin, from the y-intercept, I look at my slope, which is 2 over 1, and it's positive. I have a rise of 2. Rises up and down. I can go up or down, it doesn't matter. If I choose to go up, I have a run of 1, and it needs to be positive. So would I go left 1 or would I go right 1? To the right. Visualize. If I go to the left and connect those 2 points, that's going to be negative slope, right? So I go up to right 1, or I can go down to left 1. It does not matter. And I know you only need 2 points to make a line, but when I want to know exactly where they cross, a lot of times I'm going to put even more points just to be more accurate. You may have questions about that one. All right, now let's look at y equals 2x minus 6. What is my y-intercept? Negative 6. What is my slope? 2 over 1. And it's positive. Rise of 2, run of 1, make it positive. So notice both equations had the same slope. Are they going to be the same line? No. What if they had the same slope and the same y-intercept? Would they be the same line? Yes. But these have the same slope, but different y-intercepts. So they're not the same line. So on your y-axis, go down to negative 6. From that point, we'll count our slope. Rise of 2. So up 2 or down 2, it doesn't matter. If I go up 2 and need a positive slope, do I go left 1 or right 1? Right. So up 2, right 1. Up 2, right 1. Up 2, right 1. Or down 2, left 1. If I keep on going, am I ever going to intersect my purple line? No. What do we call 2 lines that never intersect? Now, are they never going to intersect because my graph is too small and they're going to intersect somewhere off the page? No. They have the same slope. So when one goes up 2, the other one goes up 2. When one goes right 1, the other goes right 1. Does that look like left on my screen? It's right to me. I don't know if it's opposite. Okay. They're parallel. They have the same slope, but different y-intercepts. So they're never going to intersect. So what do we put for the answer? The answer is where they intersect. Would we say 0? No solution. They're never going to intersect, so they don't have a solution. Yes? Sorry, what? Yeah. All right, so the solution is no solution. These lines are parallel, therefore they will never intersect. These lines are parallel, therefore they will never intersect. And then I just put no points, or I should say ordered pairs, in common. So I've showed you every possible number of solutions you can have, okay? You can have either one solution, and this is when you're talking about lines only, because we'll get to where we graph a line and a parabola, maybe a line and a circle, that's different. But when you have 2 lines, you're either going to have one solution, they intersect one time. You're going to have infinitely many solutions where they are the same line, or you're going to have no solution where they're parallel, they're never going to intersect. So if they intersect one time, the answer is the ordered pair where they intersect, okay? A lot of times, say kids will get a problem like this, and they'll tell me the answer is parallel lines. The answer is not parallel lines, the answer is no solution, okay? Not parallel lines, they're parallel, therefore there's no solution. Does that make sense? All right, anybody have questions about this? All right, I'll leave this up, and I'm going to pause the video. If I can remember how. Oh.